So next, we will show that the Sorgenfrey line is not second countable. So proof. Let script B be a basis for the lower limit topology on the reals. Since the half open interval from x to x plus 1 is an open neighborhood, of the point x, there exists an element b sub x in the collection script B such that x is in this element, which is contained in the half open interval from x to x plus 1. So notice that the point x is the infimum of the set b sub x, the basis element containing it. So if the point x is not equal to the point y, then the basis element b sub x is not equal to the basis element b sub y, since once again the point x is the infimum of the set b sub x, and the point y is the infimum of the set b sub y. And so every basis for the lower limit topology on the reals has at least the cardinality of the reals, that is, uncountably many elements, and hence the Sorgenfrey line does not have a countable basis. And therefore, the Sorgenfrey line is not second countable. So notice that the second countability condition is another topological property that distinguishes the Sorgenfrey line from the real line, since the real line is second countable, and the Sorgenfrey line is not. The Sorgenfrey line is not homeomorphic to the real line. So next, we will show that the Sorgenfrey line is first countable, so proof. let the collection script b sub x be the collection of all half open intervals of the form x to x plus 1 over n, where n is a positive integer. Then clearly the collection script b sub x is countable, as it has the same number of elements as the set of positive integers. Now let x be a point in the set of reals, and let the set U be an open neighborhood of the point. Then there exists a basic open set of the form the half open interval from x to b, such that the point x is in this half open interval, which is contained in the open set U. Now, since x is in this half open interval, x is less than b, and so there exists a positive integer n such that x plus 1 over n is less than b. That is, there exists a half open interval of the form x to x plus 1 over n in the collection script b sub x, such that the point x is in this half open interval, which is contained in the basic open set, the half open interval from x to some endpoint b, which is in turn contained in the open set U, and hence the collection script b sub x is a neighborhood basis at the point x. Further, this neighborhood basis is countable, and therefore the Sorgenfrey line is first countable. So next, we will show that the set of rationals is dense in the Sorgenfrey line. So proof: let A and B be two real numbers such that A is less than B. Then there exists a rational number Q that is greater than A and less than B. And so the rational number Q is in the half open interval from A to B. That is, every basic open set in the Sorgenfrey line intersects the set of rationals. And since every non-empty open set U in the Sorgenfrey line is a union of basic open sets, the intersection of any non-empty open set U with the set of rationals is not empty, and therefore the set of rationals is dense in the Sorgenfrey line. And so the Sorgenfrey line is separable as it contains a countable dense subset namely the set of rationals. So next, we will show that the Sorgenfrey line is a normal space So proof. Let E and F be disjoint closed sets in the Sorgenfrey line. Since the complement of the set F is open, for every point x in this open set, there exists a basis element of the form the half open interval from A to B, such that point x is in this half open interval, which is contained in the complement of the set F. That is, for every point x in the complement of the set F, there exists a basis element containing the point x that does not intersect the set F, and similarly, for every point in the complement of the closed set E, there exists a basis element containing the point x that does not intersect the set E, Now, since the closed sets E and F are disjoint, the set E is contained in the complement of F, and the set F is contained in the complement of the set E. So for every point E in the set E, choose a basis element, which we will denote the half open interval from E to some endpoint x sub E that does not intersect the set F, and for every point F in the closed set F, choose a basis element, which we will denote the half open interval from F to some endpoint x sub F that does not intersect the set E, then the set U, which is the union of all basis elements containing the points of E that do not intersect the set F, and the set V, which is the union of all basis elements containing the points of F that do not intersect the set E, are open neighborhoods of the closed sets E and F, respectively. And if these neighborhoods are disjoint, then the space is normal. So suppose to the contrary, that there exists a point Y in the intersection of U and V, then the point Y is in the set U, and the point Y is in the set V, and as the point Y is in the set U, Y is in the half open interval from E to some endpoint X sub E for some point E in the set E, and as the point Y is in the set V, Y is in the half open interval from F to X sub F for some point F in the closed set F. That is, point Y is in the intersection of the half open interval from E to X sub E with the half open interval from F to X sub F. And so Y is greater than or equal to E and strictly less than X sub E, and Y is greater than or equal to F and strictly less than X sub F. Now since E is less than or equal to Y, and Y is strictly less than X sub F, E is strictly less than X sub F, and as F is less than or equal to Y, and Y is strictly less than X sub E, F is strictly less than X sub E. Now let X sub naught be the larger of the two real numbers E and F, and let Y sub naught be the smaller of the two real numbers X sub E and X sub F. Then Y is greater than or equal to X sub naught and strictly less than Y sub naught. And so the point Y is in the half open interval from X sub naught to Y sub naught, which is contained in the intersection of the half open interval from E to X sub E with the half open interval from F to X sub F. Now if X sub naught is the element E, then the half open interval from X sub naught to Y sub naught intersects the set E, and hence the half open interval from F to X sub F intersects the set E. Since the half open interval from X sub naught to Y sub naught is a subset of the half open interval from F to X sub F, and if the element X sub naught is the real number F, then the half open interval from X sub naught to Y sub naught intersects the set F, and hence the half-open interval from E to X sub E intersects the set F. Since the half-open interval from X sub naught to Y sub naught is a subset of the half-open interval from E to X sub E. In either case, we have a contradiction. And hence, by contradiction, the intersection of U and V is empty, and therefore the Sorgenfrey line is normal.